for the notification that it started. There we go. So I've put a couple of important items in the chat. So test 1 is going to be on Wednesday, 9/23. That is 2 weeks from today. I will be doing a limited amount of reviewing on that Monday. I can't review for the entire class period because we have a lot of material to cover in the course. So I really will need to do some of that on that Monday as well. And I will be posting quiz 1 later today in MyLab Math. So quiz 1 will be some problem types that I've selected from our first 3 assignments, and I will put those in a quiz. Now, the quizzes are great places to review and look for test problems. So all the test problems will come from the quizzes. You'll have quiz 1 that will be posted later today, and then there'll be another quiz posted before the test. So those are great ways to review from the test. All problems or types on the quizzes will be problem types that you've seen before in the homework assignments. So I like to do it this way, where the students see the homework, these problems in the homework assignments, they see them in the quiz, they see them on the test, and some of them on the test, and also possibly on the comprehensive final. So I like to get you to look at those problems several times by the time the comprehensive final rolls around. Anybody have any questions on what I just spoke about?
Not necessarily that, but I don't know if you got that email. I'm supposed to be getting an email from the Pearson people. My access code is not working. Like, it tells me it's been used, but I just opened it, basically.
Okay, so I guess we need to talk offline about that, because I haven't had time to, I didn't even, I would like to do some investigation of my own to see what's going on.
That's fine. They said it's supposed to be fixed today. I'm just letting you know ahead of time.
Okay, so if it's fixed today, please just shoot me a quick email that it's fixed, okay?
Yes, ma'am.
So I will take a look when I have time. I have another class after this, a trig class, so I'm just jotting myself down a little note. Yes, Pearson. We've been having trouble in our trig courses with Pearson this semester. So luckily we're not seeing that in the survey of calculus course.
Yeah,
so
my access code says that it expired.
Right. So 2-week access codes, temporary codes expire. You will need to buy a permanent code. And you can buy a permanent code online.
Okay.
Okay?
Mm-hmm.
So any other questions or comments? So let's take a look at today's PowerPoint presentation, and then I also hope to show you a problem in MyLab Math that I've written out for you and go over it. So if you've got your graphing calculators handy, we will need those for that problem. So that will be later on today. That'll be at the end, near the end. So let's take a look at the PowerPoint. So we are still working in chapter 1 of the book that this course is based on, which is available as an ebook in MyLab Math. We are going to look at section 1.4 on differentiation using limits of difference quotients. We've already looked at the average rate of change. That's like your average speed going from Bentonville to Fayetteville. Now, when a police officer uses a radar gun and gets a speed at one specific instant in time, that's called an instantaneous rate of change. And we are going to be looking at instantaneous rates of change today. what is our objective? Find derivatives and values of derivatives. So we're going to have to talk about what a derivative is. Find equations of tangent lines, and we will need to talk about what a tangent line is. So let's move along. So first of all, we have a picture here, and we have a nice curve right here. And at this point P, you will notice that there's this red line through this point P, and it's labeled with a T. That's because it's the tangent line at point P. What is a tangent line? A tangent line is a straight line that approximates the curve on both sides of a point. So if we go a little bit to the left of point P, you can see that this tangent line, this red line here, still looks like it's really almost identical to the curve in that small little bit past P on the left. Same on the right. So this infinitesimal amount of this pink line on the right, it looks like it's approximating the curve very well. So this tangent line is a unique line that best approximates the curve on both sides of a point, in this case, P. Also, to talk about tangent lines, the slope of a tangent line must exist. So over here it says slope M, we use M for slope, equals the limit as h goes to 0 of this difference, and then we have a quotient. So the way we find slopes of tangent lines is we find the limit as h goes to 0 of f of x plus h minus f of x over h. This is a difference quotient inside here. And then we take the limit as h goes to 0. Now, if you just plug in 0 here, you're going to get division by 0, and that's not going to work. So there's more work to do than might meet the eye here. So I also want to remark that the slope of the tangent line must exist in order for there to be a derivative at point P. And we're going to talk about derivatives today and for a long time in this course. So the slope of the tangent line at x comma f of x, so x is the x coordinate, this f of x is the y coordinate, is slope equals this, which we just mentioned. This limit is also the instantaneous rate of change of f of x at x. So it's also an instantaneous rate of change. It's at the rate of change at the instant when we are looking at the x coordinate of point P. It's that instantaneous rate of change at the point, more precisely, x comma f of x at this point. And an instantaneous rate of change turns out to be the limit of these guys, which are average rate of change. So that's another way to look at the instantaneous rate of change. It's the limit of these guys here, these average rates of change as h gets closer and closer and closer to 0. And please feel free to unmute your mics and ask me questions as we go along. I'm going to move on here. So let's talk some more about this. For a function y equals f of x, its derivative This is the definition of derivative for this entire class, which we're going to work with all kinds of derivatives in this class. The derivative of a sum, the derivative of a difference, the derivative of exponential functions, the derivative of polynomials, the derivative of natural log functions. We're going to look at a lot of different types of derivatives in this class. So for a function y equals f of x, its derivative at x is the function f prime. This little prime up here, that's the notation that indicates that we want the derivative. The derivative of what? The derivative of the f function. And to be precise, we want the first derivative of the f function. We are also going to talk about second derivatives in this class, and then there would be 2 primes. So with 1 prime, it means the first derivative of the f function. So it's defined to be f prime of x equals this limit that we just talked about, provided the limit exists. It may not exist. For instance, if the tangent line that best approximates the curve at a point, if it's a vertical tangent line, the slope of a vertical line is undefined. So that's a case where it wouldn't exist. So provided the limit exists, if f prime exists, then we say that f is differentiable at x. In other words, it has a derivative. We use the word differentiable. And you can see at this point, this pink line approximates this curve a little below it and a little above it. And that's exactly what a tangent line is. It's a straight line through the point that we're talking about, the point we want to find the derivative at, let's say, that best approximates the curve on both sides of the curve. It's a unique line, and its slope must exist for there to be a derivative at x in this case. And if there's a derivative at x, this is how we can find it. Let's go on. So let's take a look at a little example here. We're going to start out just basic and work our way up. So we're just going to look at the function f of x equals x squared, which is a parabola sitting on the origin that opens up. We want to find f prime of x. Then after we find the first derivative at x, which is what this is, then we're going to take that first derivative function and evaluate it at -3 and at +4. So this is how we find the derivative. So the first thing we want to do for the function that we're finding the derivative at, we want to find f of x plus h. What is that? So we want to find what is the y? F is you can think of as the y coordinate. We want to find the y coordinate when the x coordinate is x plus h in this case. So I'm going to take this x plus h and plug it in for x up here and get x plus h squared. And that's where this x plus h squared is coming from. Then it says minus f of x. Well, f of x is clearly stated as x squared here. So minus x squared all over h. And of course, I forgot to mention the limit as h goes to 0. So this is what we are dealing with. So let me just click here. So this x plus h squared, this exponent of 2, really means we have two of these x plus h multiplied together. So we have x plus h times x plus h. So this entire expression here means x plus h times x plus h. That's a binomial times a binomial. So you can multiply that out using FOIL, the first two. So we would have, you can write down, and it may help if you write down x plus h with parentheses around it times x plus h with parentheses around it. The first two is x times x, which is x squared. So that's where they got this x squared. The outer two is x times h. The inner two is h times x. Now, we of course, multiplication, we can multiply in any order. So I can take the hx and switch it to xh, and then I would have xh plus xh, which is 2xh. And then the last two would be h times h, which is h squared. And then minus this x squared here over this h and the limit notation right here. So we're talking about the derivative here. The derivative is equal to this. So let's see what we can do. So x squared and minus x squared were crossed out because they sum to 0. So what's left up here in the numerator? This term and this term, we have each term here that's left has an h in it. So we can factor that h out. So that's why they factored an h out here. If we take this h out and cross that out, we have a 2x left in here. Okay, and plus, if we take, there's h, this is really h times h. So one of the h's is coming out front, and then there's this other h's left inside. What does that h over, now what did that h do for us? It allows us to cancel this h can be canceled with what's in the h in the denominator, which is really nice because now we don't have a denominator other than an understood one. So now we are just needing to find the limit as h goes to 0 of 2x plus h. So our derivative is now the limit as h goes to 0 of 2x plus h. What should I do with that 0? Can anybody tell me what I should do with this 0 here? This is the limit as h goes to 0. Where should I put that 0? Where does it go in?
And the x
Where do I put the 0? In for what?
for the x?
No, because it has the h's go to 0. It doesn't say x goes to 0, but good try, good try. It doesn't say as x goes to 0 here. It says as h goes to 0. So we put the 0 in for h. And when we put the 0 in for h, we get that h is wiped out and we just have 2x left, and that's why the first derivative of x is 2x. We have a nice little formula there to calculate a bunch of derivatives if we want to. And I appreciate you stepping up to ask that question, because sometimes there's more learning to be done if you get an answer wrong than there is if you get it right. So that's really important. So now we have our first derivative formula. We have a formula to be able to now find the slopes of any tangent lines we want. So that's really, really, really good. So let me go on. I don't think there is a, yes, let's go on. So the first derivative of x is 2x. So they're just writing that over again. Now, they've asked us to find the first derivative at -3. So once you have this, you have a first derivative function here. You can find rapidly the first derivative at a bunch of different x's. That is, you can find the slope of the tangent line to the curve at a bunch of different x's quickly. So let's find it at x equals -3. So all I do is take this -3, this is my x here, and we plug it in to x here, and we get 2 times x, which we're using -3, so we get 2 times -3, which is -6. So this says that the slope of the tangent line at x equals -3 is equal to -6. In other words, we've got a downward sloping tangent line because the slope because the first derivative is negative, and the first derivative stands for the slope of the tangent line. Now we can do another one just to prove that we could put any number in here that we want. So what's the first derivative of 4? Well, 4 is our x here. So we take 2 times x, which is 4, and get 8. So my point here is that this is a function now. That's why we have the f notation here. But the prime tells us we want that we are talking about our first derivative function. I'm debating on whether I want to do this one. I don't think I do, but I might come back and do it.
Can I ask you what it is?
What's the question?
I was gonna ask if I think I know what it is.
When you say think you know what it is, if you already know derivatives, you still will be tested on using the process here, okay? So do you already know derivatives and that's why you know what it is, or do you understand this whole process here? I guess is what my question.
Both. I was just gonna try to solve it.
Oh, you were going to try to solve it? Okay, well, let's look at it then. I don't have a problem with that. So we are now talking about f of x equals x cubed. So what do we need to do first? We need to start with f prime of x equals the limit as h goes to 0 of this difference quotient here. It's a difference because it's a subtraction, and it's a quotient because of this division symbol here. So the first thing to do is to, and just hang on there, I'll ask you for your input in a minute. The first thing to do is to put x plus h in for x here. And then you're going to get x plus h cubed right here. And then minus f of x is just f of x is x cubed. Okay, so can you tell me what do we do with this x plus h cubed?
You multiply it out 3 times. You can do.
Yes.
Yeah.
Yes, that's absolutely true. You're absolutely correct. We want 3 of the base multiplied together. So we want x plus h times x plus h times x plus h. So the way to handle that at first is you can write down x plus h times x plus h times x plus h with parentheses around each of the x plus h's. And then you could just look at the first 2 and multiply those together using FOIL because we have 2 terms times 2 terms. If we multiply those together using FOIL, the first 2 is x times x, which is x squared. The outer 2 plus xh, the inner 2 plus plus hx, and the last 2 plus h squared. Now the xh and the hx can be combined because you can switch the order of multiplication. And now we have x squared plus 2xh plus h squared. But we need to multiply that by x plus h. So let's put x plus h in front. And so what we need to do there, we cannot FOIL those 2 together because x squared plus 2xh plus h squared have 3 terms. FOILing only works for 2 terms times 2 terms. So what we can do is, since we have the x plus h in front, we can take that x and we distribute that x through those 3 terms. So we get x times x squared, which is x cubed. We would get x times 2xh, which is 2x squared h. And then we would get x times h squared, which is xh squared. And then after that, we would then distribute the h through all those 3 terms, and we would get hx squared plus 2x h times h, which is h squared, plus h times h squared. So we have 1h, 2 more inside, that's a total of 3. So we get h cubed. So we're looking at now combining like terms. So we definitely have this 8x cubed here. How did they get the 3x squared h? So there's a term that's 2x squared h, and there's a term that's hx squared, which we could write as x squared h. So those 2 would combine to give us 3x squared h. So let me check those off so we make sure I don't look at them again. And then where did this term come from? So there's a term, xh squared, and then another term, 2xh squared, but I'm going to switch that one. I'm going to change the order of multiplication to, I guess, no, I don't need to change the order of multiplication there. So I have xh squared and 2xh squared, so we have 3 of those xh squared right here. So it's important to understand this process because the process may come up in your homework problems. And then lastly, we have an h cubed, a lonely h cubed. So that's where that's coming from. So these first 4 terms here, right here, came from this right here. And then we have minus x cubed. So we had to copy that down over h. So you're absolutely right. I mean, this x cubed here helps us that's great because that makes us cancel these. But it's real important to know what we have in the middle here. And if you notice, each term in the middle has an h in it. It has at least one h in it. This has an h, this has an h, this has an h. So the next step would be to factor out that single h. And we only need to factor out a single h because there's only a single h in the denominator. And what we're looking for is a single h upstairs to cancel this one downstairs. So you will notice what they've done here is they factored out a single h. So if we factor a single h out of this term, that goes, we're left with 3x squared. If you factor a single h out of this term, one of the h's goes, but one stays, so we have 3xh left. We're taking one of these h's out, so we have 3 minus 1, which is 2 of them left. And then we copy this h down. So what does that do for us? H divided by h is 1. And 1 times what's left is just what's left, which is what's in parentheses here. So that just has been copied over. And of course, we need to carry along the limit as h goes to 0. So where do we put this 0 at? What does it go in for? And how many terms do we put 0 in for? Can somebody answer those questions? Where does that 0 go now?
Did you put x or no?
So what is this variable? That variable here. That's h. So h goes to 0 means we can put in the 0 for only h.
Oh, I'm tripping.
So that's good though, because this is emphasizing the importance to look what your variable is when you're taking the limit. That's what you can put the number in for. So we have two h's here we can put this in for. This 0 can go in for this h and for this h. So what does that mean? If we have a 0 here, 0 for h, 0 times what's left is what's left. Okay, so 0 times 3x is 0, is my point. And if I put a 0 in and square it, we get 0 times 0, which is 0. So these two terms are now gone. And we're just left with 3x squared. So our limit is 3x squared. And since our first derivative of x is equal to that limit, our first derivative of x is equal to 3x squared. So you will see some somewhat challenging homework problems on finding the difference quotient. Or on, yes, and then taking the limit. So you will see one of those on your first test where you've got to show the written work. For 7 of the questions on your first test, you will be showing the written work and submitting it to me in Canvas. I will tell you what those 7 questions are, but you're not going to get anything this time consuming. We have an hour and 15-minute class. So any questions before we move on here?
So for the most part, all of this is just factoring?
Well, it's not factoring really, it's multiplying out, which is the opposite of factoring.
Oh.
Okay, but you're on the right track. So let's look here. So we found our first derivative at x. We have a nice formula here, if you will. So let's look at what the slope of the tangent line to the curve at x equals 1 is. So we just take the -1 rather, and plug it in for x here. And we get 3 times -1 squared because we're plugging in the -1 in for x. So we then have to put parentheses around the -1 because of the negative sign and square it. So this square represents -1 times -1, which is +1. And then we've got to carry the 3 along, and we get 3 times 1, which is 3. So the slope of our tangent line at x equals -1 is 3, which means we have our tangent line is going up as we go from left to right because it's a positive number. So remember, positive sloping lines go up, negative sloping lines go down. So let's see what we've got here. And then we're just doing it again. This time, they didn't actually put in the number here. They should have put in 1.5 over here, but the process is exactly the same. You put 1.5 in here, square it, and then multiply it by 3. And if you do that math, that's what you would get. The math part of it here isn't as important as the point is that once you find a first derivative function, you can use it to find the slope of lots of tangent lines rapidly. Also, the first derivative is the instantaneous rate of change at x. So at that one moment in time that the police officer is shooting his, putting up his radar gun and trying to get the speed of the car of the car that he wants, that's what we're also talking about it. So there's several different interpretations of the first derivative. They all mean the same. It is the slope of the tangent line. It is the instantaneous rate of change. And in this course, if it doesn't mention what rate of change you use, the default is instantaneous rate of change. So if you're asked to find the rate of change in a problem, the default is instantaneous, not average, instantaneous. Mostly in this course, we're going to be talking about instantaneous rates of change. The only reason we talked about average rate of change is because the instantaneous rate of change is the limit of average rate of changes, I should say. So going on, and please interrupt me. We definitely want to take a look at this one. There's one similar that came up in the problems that I printed off and did, and I believe it was either 2 over x or 4 over x. So let's take a look at this one. Just do a quick look at the time here. We're good. So how do we start? We want to find f prime of x. So we want to find the limit as h goes to 0 of the difference quotient. We also, after we do part